Assalamu alaikum. Welcome to the class of electromagnetic field theory. We are going to talk about the first chapter, and the first chapter is related to vector quantities. So let us define a vector quantity. Any quantity that can be described by magnitude as well as direction is known as a vector quantity. So vector quantity has a magnitude as well as direction. Mathematically, we represent a vector quantity with the help of equation number 1.1. Vector A is represented with the help of equation number 1.1, and the first quantity on the right hand side represents the magnitude of this vector quantity, and small a represents the unit vector in the direction of vector A. So small a is a unit vector in the direction of vector A. If we want to find out the unit vector in the direction of vector A, we play with equation number 1.1, and we can find out the unit vector A, which is in the direction of vector A, with the help of equation number 1.2. So vector A divided by the magnitude of this vector will give you the unit vector in the direction of vector A. So this is how we represent a vector quantity mathematically. Let us talk about the graphical representation of a vector quantity. So the graphical representation of a vector quantity is shown in figure 1.1. The magnitude of this vector quantity is given by the length of this arrow. The length of this arrow gives you the magnitude of this vector quantity, and the head, which is in the form of an arrow, gives you the direction of this vector quantity. So this is the graphical representation of a vector quantity. The length of this arrow gives you the magnitude, and the head of this arrow gives you the direction of this vector quantity. We know that the addition of two or more than two vectors results in a new vector quantity. So we consider two vectors A and B. We add two vectors according to head to tail rule. The addition of two vectors in accordance with head to tail rule results in the new vector. So A plus B is equal to C. And we know that the addition of two vectors obey commutative law. So we can change the order of these two vectors. We can consider either vector A first or B first. The resultant vector does not change. So B plus A will also be equal to C. It means that vectors obey commutative law with respect to addition. The addition of two vectors obeys commutative law. So in this diagram, we add these two vectors in accordance with head to tail rule. So we are adding vector A and B in accordance with head to tail rule, and the addition of these two vectors results in vector C. In order to prove commutative law, we change the order of these two vectors. Now we add B and A in accordance with head to tail rule, and the addition of these two vectors according to head to tail rule results in the same vector, that is C. So you see, we can add two or more than two vectors in accordance with head to tail rule, and the addition of vectors obey commutative law. We can change the order of the vectors. The result does not change. Scalar product. The scalar product is also known as dot product. And the scalar product results in a scalar quantity. And this dot product or scalar product obeys commutative law. It means that we can change the order of the two vectors in case of the scalar product. The result will not change. So let us consider two vectors A and B. The angle between these two vectors is theta. We are going to calculate the scalar product or the dot product of these two vectors, and we know that the scalar product of the two vectors obeys commutative law. So we can change the order of these two vectors. A dot B will be equal to B dot A. The vectors are represented with the help of bold letters in this course. So A dot B will be equal to B dot A, and it will be equal to the magnitude of A multiplied by the magnitude of B multiplied by cos of the angle between these two vectors. So the magnitude of A multiplied by the magnitude of B multiplied by cos of the angle between these two vectors results in the scalar product, and it gives you a scalar quantity. You know that AB cos theta is a scalar quantity. It's not a vector quantity. Now what we do, we consider two vectors A and B, and we assume that these two vectors are equal in magnitude and they are in the same direction. So B in this particular case is equal to A. So definitely A dot B will be equal to A dot A, and A dot A will be equal to the magnitude of A multiplied by the magnitude of A multiplied by cos of the angle between these two vectors. And we know that cos of the angle between these two vectors is 0. The angle between these two vectors is 0, so cos of 0 will be equal to 1. So a dot a will be equal to a square, and we can calculate the magnitude of this vector with the help of equation number 1.8. So the magnitude of vector a will be equal to under root a dot a. So this is how we calculate the magnitude of a vector quantity. The magnitude of vector b will be equal to b dot b. Similarly, the magnitude of vector c will be equal to c dot under root c dot c, and so on. So this is how we calculate the magnitude of a vector quantity. The vector product. This product is also known as cross product. The cross product of two vectors obeys commutative law. We consider two vectors a and b. The angle between these two vectors is theta. We want to find out the cross product between these two vectors, and the cross product of the two vectors does not obey commutative law. A cross b is never equal to b cross a. So the cross product results in a vector quantity. The cross product of two vectors results in a new vector quantity, which is represented by C in equation number 1.9. So A cross B, which results in vector C, will be equal to the magnitude of A multiplied by the magnitude of B multiplied by sine of the angle between these two vectors, that is sine theta, multiplied by the unit vector an. So this unit vector an is normal to the plane containing a and b. If these two vectors are in the plane of the board, in the plane of the screen, then the resultant vector will be normal to the screen. And if you want to find out the proper direction of the resultant vector, we apply the right-hand rule. How do we apply right-hand rule? I shall explain this right-hand rule in the line in the online session for this particular lecture. So vector C, the resultant vector, will be normal to the plane containing A and B. So let us explain the right-hand rule. If we want to find out the direction of the resultant vector A cross B, you see vector A is coming first. So we place our right hand along with the first vector, that is A. In this particular case, your thumb should be normal to the fingers. So we place our right hand along with the first vector. We move our right hand towards the second vector in such a way that the front side of our right hand faces the second vector. If the front side of the right hand faces the second vector, then the thumb in this particular case represents the direction of the resultant vector. Similarly, if you want to find out the direction of the resultant vector in case of B cross A, so you see vector B is coming first. So we hold our right hand along with the first vector B in such a way that the front side of our right hand faces the second vector A. If we move our right hand from the first vector towards the second vector, the front side should be facing the second vector. The front side of our right hand should be towards vector B. It should be facing vector B. So in this particular case, the thumb represents the direction of vector C or the resultant vector. We know that A cross B is equal to minus B cross A. This means that the vectors do not obey commutative law in case of cross product. Let us talk about the rectangular coordinate system. In the rectangular coordinate system, we consider three coordinates: the x coordinate, y coordinate, and z coordinate. All these three coordinates are normal to one another. You see there is an angle of 90 degree between x and y. There is an angle of 90 degree between y and z, and there is an angle of 90 degree between x and z. So there are three coordinates in the rectangular coordinate system: the x coordinates, the y coordinate, and the z coordinate, and these three coordinates are mutually orthogonal. The angle between two coordinates of this rectangular coordinate system will be 90 degree. The angle between x and y is 90 degree. The angle between y and z is 90 degree. And the angle between z and x is 90 degree. So all these three coordinates are normal to one another. They are mutually orthogonal. What we do, we are going to find out the location of a point in our three-dimensional space with the help of this rectangular coordinate system. The point is represented by P. In all, the three coordinates of this point are known. We know the x coordinate of this point, the y coordinate of this point, and the z coordinate of this point. If we consider this rectangular coordinate system, which is shown in figure number 1.8, you guys can see three planes in this rectangular coordinate system. You guys can see z is equal to 0 plane, you guys can see x is equal to 0 plane, and you guys can see y is equal to 0 plane. So there are three planes in the rectangular coordinate systems. In this rectangular coordinate system, z is equal to 0 plane. This z is equal to 0 plane is also known as xy plane. X is equal to 0 plane is also known as yz plane. And this y is equal to 0 plane is also known as xz plane. So there are three planes in this rectangular coordinate system. X is equal to 0 plane or xy plane. Z is equal to 0 plane or xy plane. X is equal to 0 plane or yz plane. Y is equal to 0 plane or xz plane. So we want to find out the location of this point in the rectangular coordinate system. So what we do, we take the x coordinate along x-axis. We take the x coordinate of this point along x-axis. Then we consider the y coordinate of this point parallel to y-axis. And if you consider this point is in the z is equal to 0 plane. Then from this point, we move parallel to z axis such that the length of this point is z is equal to z coordinate. So we reach this point, which is represented by P. So what we do? We consider the x coordinate of this point along x-axis, the y coordinate of this point along, not along, parallel to y-axis, the y coordinate of this point parallel to y-axis, and then the z coordinate of this point parallel to z-axis, and we reach this point, which is represented by Pxyz. So this is how we find out the location of a point in the rectangular coordinate system. There are three unit vectors, ax, ay, and az in the rectangular coordinate system. The unit vector ax is along x-axis. The unit vector ay is along y-axis. And the unit vector az is along z-axis. So these three unit vectors are mutually orthogonals. They are normal to one another. The angle between ax and ay is 90 degree. The angle between ay and az is 90 degree. And the angle between az and ax is 90 degree. So there are three unit vectors in the rectangular coordinate system. The unit vector ax, the unit vector ay, and the unit vector az, and these three unit vectors are shown in figure 1.9. You see the unit vector ax is along x-axis. The unit vector ay is along y-axis. The unit vector az is along z-axis. So these three unit vectors are mutually orthogonal. They are normal to one another. You see, ax dot ax results in 1. Ay dot ay results in 1. And az dot az results in 1. So ax dot ax results in 1. Ay dot ay results in 1, and az dot az results in 1. Similarly, ax dot ay results in 0, ax dot ay results in 0. Why? Because there is an angle of 90 degrees between these two unit vectors. Ay dot az ay dot az results in 0, and similarly ax dot az results in 0. So ax dot ax is 1, ay dot ay is 1, az dot az is 1, but ax dot ay results in 0, ay dot az results in 0, and ax dot az results in 0. Let us consider the cross product of these unit vectors. You see, ax cross ax results in y, ay cross ay, ax cross ax results in 0, ay cross ay results in 0, az cross az results in 0. If we consider the cross product of ax and y, the cross product of ax and ay results in az. We can find out, you see, this resultant unit vector with the help of right hand rule. Just apply the right hand rule and you guys will come to know that the resultant vector in this particular case is az. Similarly, ay cross az results in ax. Az cross ax results in ay. We know that vectors do not obey commutative law in case of cross product. And a cross b is equal to minus b cross a. So if we change the order of the two unit vectors in this table, the resultant unit vector will change. We need to place a minus sign with the resultant unit vector. So you see, we are changing the order of the two unit vectors over here. Ay cross ax results in minus az, az cross ay results in minus ax, and ax cross az results in minus ay. We know that a cross b is equal to minus b cross a, and you guys can apply the right hand rule to find out the direction of the resultant unit vector. If we have a three-dimensional vector in a rectangular coordinate system, there will be three components of a three-dimensional vector in the rectangular coordinate system. There will be a component along x-axis, a component along y-axis, and a component along z-axis. So a three-dimensional vector in the rectangular coordinate system has three components: the component along x-axis, the component along y-axis, and the component along z-axis. And if we add these three components in accordance with head-to-tail rule, the addition of these three components results in vector A. So this is how we represent a vector, a three-dimensional vector in rectangular coordinate system. A three-dimensional vector in a rectangular coordinate system will have three components. The component along x-axis is ax. The component along y-axis is ay, small ay. And the component along z-axis is az, small az. So equation number 11 represents a three-dimensional vector in rectangular coordinate system. We know that the addition of two or more than two vectors in any system results in a new vector. And the addition of vectors obeys commutative law. So let us consider a three-dimensional vector in the rectangular coordinate system. This three-dimensional vector has three components. The component along x-axis, the component along y-axis, and the component along z-axis. We consider another vector which is represented by b, and this vector is a three-dimensional vector. And this three-dimensional vector will have three components: the component along x-axis, the component along y-axis, and the component along z-axis. So we consider two vectors. These are three-dimensional vectors, and these two vectors are in the rectangular coordinate system. We are going to add these two vectors, and we know that the addition of two or more than two vectors results in a new vector quantity. We also know that the addition of vectors obeys commutative law. So a plus b will be equal to b plus a. And in this particular case, we add the x component of a with the x component of b. It will be along x-axis. We add the y component of a with the y component of b, and this resultant component will be along y-axis. And we add the z component of a with the z component of b, and this resultant component will be along z-axis. So this is how we add two vectors in the rectangular coordinate system. Let us talk about the scalar product. So the scalar product of two vectors results in a scalar quantity. It obeys commutative law. So we consider two vectors, a and b, and we know that a dot b will be equal to b dot a. If we simplify this scalar product, we get ax bx plus ay by plus az bz. So this is how we calculate the scalar product of two vectors in the rectangular coordinate system. Let us consider two vectors which are equal in magnitude and are in the same direction. Let us consider that b is equal to a. So if b is equal to a, then a dot b will be equal to a dot a, and a dot a will be equal to ax into ax plus ay into ay plus az into ez. So this a dot a will be equal to ax square plus ay square plus az square. We take the square root on both sides of this equation, and we know that under root a dot a results in the magnitude of vector a. So we can calculate the magnitude of vector a with the help of equation number 16. The magnitude of vector a will be equal to under root square of the x component plus square of the y component plus square of the z component. We talk about the vector product. we know that the vector product results in a vector quantity. It does not obey commutative law. And we consider two vectors A and B, and these two vectors are three-dimensional vectors and they are in the rectangular coordinate system. So in order to find out the resultant of this cross product A cross B, we go for this determinant. You see, in the first row, we have the unit vector Ax, the unit vector Ay, and the unit vector Az. In the second row, we have the x component of A, the y component of A, and the z component of A. In the third row, we have the x component of B, the y component of B, and the z component of B. If we expand this determinant, the expansion of this determinant results in the naive resultant vector, which is represented by C. You see, if you guys want to calculate B cross A, you guys will have to interchange the last two rows of this determinant. You guys can expand this determinant, and this determinant will give you minus C. You see, in the first row, we have all the three unit vectors of the rectangular coordinate system, that is Ax, Ay, and Az. In the second row, now we have the x component of B, the y component of B, the z component of B. And in the third row, we have the x component of A, y component of A, and z component of A, and the expansion of this determinant will give you minus C. Why? Because A cross B is equal to minus B cross A, and obviously the vectors do not obey commutative law in case of the cross product or vector product. So, in the rectangular coordinate system, we assume that our three-dimensional space is in the form of a rectangular box. You guys can see the rectangular box in figure number 10. Here is the x coordinate, here is the y coordinate, and here is the z coordinate. So we assume that this three-dimensional space is in the form of a rectangular box. Let us talk about the limits for these three coordinates. I mean the limits for the x coordinate, the limits for the y coordinate, and the limits for the z coordinate in the rectangular coordinate system. So x extends from minus infinity to plus infinity. Similarly, y extends from minus infinity to plus infinity, and z extends from minus infinity to plus infinity. This is the first lecture of the electromagnetic field theory. I hope that you guys will understand, you see, this lecture. I will arrange an online session for you guys, and if you guys have any question, any query regarding this this lecture, I shall respond to your queries and question in the online video session. Thank you so much. We shall discuss the cylindrical coordinate system in the upcoming class. How do we represent a point in the cylindrical coordinate system with the help of cylindrical coordinates? How do we represent three unit vectors in the cylindrical coordinate system? And definitely those three unit vectors of the cylindrical coordinate system will be mutually orthogonal. How do we consider the scalar product of the unit vectors, the vector product of the unit vectors, and how do we find out the location of those three unit vectors in the cylindrical coordinate system? Then how do we represent a three-dimensional vector in the cylindrical coordinate system. Definitely a three-dimensional vector in the cylindrical coordinate system will have three components. How do we calculate the addition of two vectors in the cylindrical coordinate system? How do we find out the scalar product of two vectors in the cylindrical coordinate system? And how do we represent the vector product of two vectors in the cylindrical coordinate system? How do we calculate the cross product or the vector product of two vectors in the cylindrical coordinate system? And then at the end we will conclude that we assume that this three-dimensional space in the cylindrical coordinate system is in the form of a cylinder, right circular cylinder. And then we will talk about the limits of the three coordinates of the cylindrical coordinate system in the upcoming class. Thank you so much.